Welcome back to the deep dive. Today we are strapping in for what is, I think, the ultimate quest in AI research.
Yeah, it really is.
The creation of artificial general intelligence that doesn't just learn but actually self-evolves. We're looking at sources that propose a whole new direction for creating these next-gen intelligence systems, and they argue that these systems need an innate evolutionary capacity.
Right, sort of like biological organisms have.
Exactly.
That's right. And our mission today is really to get past the current AI landscape. I mean, we need to move beyond the incredible successes of large language models, the LLMs we all use.
Right.
We're exploring a roadmap for building agents that are truly autonomous, that are self-modifying. Researchers are calling these the foundation for second nature technologies.
Second nature technologies, what does that mean in practice?
It's about systems designed to just seamlessly integrate into our world, to make our environment comfortable, predictable, resilient even, all without constant human hand-holding.
Okay, so let's dig into the big critique this research has for the current state of things. The source material argues that modern cognitive architectures, CAs, are they're too schematic.
Too rigid.
Yeah, they rely on these predetermined patterns of perception and logic that were basically hardwired by their creators.
And if you want something that's truly general, truly evolutionary, you just can't start with a finished blueprint. It doesn't work.
So we have to figure out how to generate these core intellectual functions from the ground up, using something like a biologically inspired functional core. So let's start there with that idea of second nature evolution. I mean, we're surrounded by smart systems now.
Oh, for sure. Thermostats, cars.
Right, industrial automation.
Yeah.
How does the adaptability that these things need, how does that push us past today's narrow AI and into needing real AGI?
It really comes down to monitoring and prediction.
Yeah.
I mean, look at current tech. It's constantly evolving to interact better with us, with our environment. So if you want an AGI system to, say, manage a city's infrastructure, it needs to monitor incredibly complex signals, sudden weather shifts, seismic activity, even just local energy demand.
And not just monitor, but predict what happens next.
Exactly. It has to predict how those changes will affect the human environment. If it sees a sudden downpour is coming, it should, automatically optimize the drainage system.
Without anyone telling it to.
Without anyone telling it to. That level of proactive compensation requires true autonomy. It needs the ability to adapt to things the programmers never even thought of.
And this, I think, perfectly highlights the problem with our current AI champions, the LLMs, when you get them away from text.
It does.
Why can't we just, scale up a transformer model and solve these dynamic problems?
I think betting the farm on LLMs for this kind of analytical work is, well, it's just not going to work for a few reasons that are all about the data structure.
Okay.
Think about what LLMs eat. Language. It's based on discrete, homogeneous information words, tokens, rules of syntax. Now think about managing a power grid. That requires processing measurement results with continuous value scales, specific voltages, specific pollutant levels, and data streams from all sorts of different sensors.
So if I try to describe the difference between two air quality readings with just text, like air is bad versus air is very bad, I lose all the important detail.
You lose all the nuance you need to actually engineer a solution. You need the full continuous data set.
Right.
LLMs are about abstraction. Analytical tasks demand precision. And then second, LLMs are trained on static pre-trained data. The world isn't static.
No, it's constantly
The
changing.
pre-training just can't keep up with the pace of reality.
And the final, maybe the biggest constraint,
Yeah, this is the big one.
is that current methods only process data about the world as humans perceive it. It's all filtered through our senses, our labels.
Yes. And if AI is going to evolve into a fully autonomous system, that second nature, it has to be able to expand its perception beyond ours. LLMs are stuck with human perception. AGI has to evolve its own.
That brings up maybe a slightly scary question. If an AI develops its own independent senses, its own cognitive map, its own way of seeing the world, how do we ever guarantee it's aligned with us?
And that is the core philosophical and engineering challenge of this entire field.
Yeah.
It suggests we have to control the process of its development, not the final result.
Okay, before we go there, let's frame the existing approaches. We have weak AI.
Right. Systems for narrow tasks, like maybe a tutoring system that integrates emotion.
And then the big prize, AGI.
The AGI direction, which aims to reproduce all cognitive functions. You see this in projects like LIDAL-I or ACTR. But the real challenge, and this is why we're doing this deep dive, is that there's just no generally accepted unifying theory for how to do it.
That lack of a theory leads us right to the biggest roadblock in AGI, the semantic hurdle. Historically, we've tried, what, 3 main ways to model intelligence?
That's right. You start with the symbolic or the top-down approach. This is classic AI. It's all about manipulating symbols based on a predefined alphabet, like in architectures such as EPIC or Icarus. The strength is formal logic.
But the weakness is that its cognitive abilities are permanently trapped by that initial set of characters you gave it.
It's a closed system. It can never define a truly new concept. Then you have the opposite, subsymbolic or bottom-up.
Which is where neural networks mostly live.
Exactly. Here, symbols are supposed to arise from processing huge amounts of sensory data, and its strength is amazing pattern recognition. But there's a hidden weakness.
Which is?
Even though the symbols seem to emerge on their own, there's always an implicit, preset meaning in the data.
You mean the human programmer already defined the categories?
Yes. If you train a network on cat photos, you've already provided the label cat. The symbol might emerge, but its meaning is totally dependent on the human who fed it the data. It's pre-grounded.
And trying to bridge that gap gets you to hybrid architectures, which combine the two, but they all slam into the same wall, which is the symbol grounding problem, SGP.
And this is where it gets really critical. FGP is the hard problem. How can an autonomous agent define its own symbols based purely on what it perceives with no human help? Current systems work by syntactic manipulation. They have rules about how symbols relate to other symbols.
But manipulating rules isn't the same as understanding meaning. I can learn the grammar of a language without knowing what a single word means.
Precisely. Thinking is about manipulating meanings, not just symbols. And when we look at this as a developmental process, how a mind grows over time, SGP is often reformulated as the symbol emergence problem, SP.
So SGP is the static philosophical problem, and SEP is the dynamic engineering challenge.
That's the key. And the source material argues that for true AGI, the thing it has to process is the meaning itself. And you can't cheat. No predefined semantic resources, internal or external. It has to come from scratch. So since that old engineering approach has basically hit a wall, the author suggests we turn to the science of science semiotics to figure out how meaning is actually built.
Right, we have to simulate the dynamics of how cognitive functions develop, not just copy their final structure.
We have to get past that reductionist focus on just neurophysiology and look at subjective reality. So let's run through the key terms.
Let's do it.
First, you have the umwelt. This is the agent's self-centered world, its own subjective perception bubble.
Okay.
And inside the umwelt, you have 2 parts. First, the Merkwelt, which is the perceptual world, what the agent's sensors are actually picking up.
The second.
The Workwelt, that's the operational world, what the agent can physically do, the levers it can pull.
And the interaction between what it senses and what it can do creates the third piece, the Innenwelt.
The Innenwelt is the cognitive map. It's the world as represented in the agent's internal sign system.
Yeah.
And the process that connects them all is called semiosis.
Okay, so give us an example of semiosis.
Think of Pierce's model. A newborn sees a hot stove. That's the object. The heat registers as a sign, the representament. That leads to a feeling of pain or danger, the interpretant or the meaning.
And that meaning then becomes a new sign for the next interaction.
It creates a continuous loop of meaning-making. And that interpretant, that raw meaning, is what starts to build the Innenwelt.
Which brings us to constructivist AI, based on Jean Piaget's work.
Piaget's big idea was that intelligence is adaptation. It's about seeking balance, homeostasis, with your environment. For a machine, the core of this is the schema mechanism.
That's a triple, right?
A triple. The context it's in, the action it takes, and the expected result of that action.
And the 2 processes that drive the whole thing are assimilation and accommodation.
Right. Assimilation is trying to cram new data into your existing schemes. You see a new 4-legged animal and call it doggy because that's the scheme you have.
Forcing a square peg into a round hole.
Exactly. Accommodation is when you realize the old scheme doesn't work. Maybe this new animal meows. And you modify the scheme itself. You create a new kitty category. That ability to self-modify is true learning. That's how the Innenwelt grows from nothing.
Okay, so this foundation leads to a new kind of architecture, one that's split into 2 layers.
Right. You have the interface layer for direct interaction with the world.
The perceptual and motor parts.
And then you have the mental function layer for abstract stuff, the intelligent, emotional, and volitional components.
Let's quickly go through those 5 core components.
Okay, perceptual is easy. It just provides raw sensor data. The motor component handles control and action. But wait, the motor component is actually the central hub.
How
It
so?
transfers information between all the other core components. It's the main communication bus for the whole system.
Interesting. So it's low level in function, but high level in its architectural role. Then you have the intelligent component.
That's the Innovel manager. It creates, modifies, and stores all those mental models and symbols.
And here's where things get really different from classical AI, the emotional component. You're saying it has a huge role in self-supervised learning.
It's a learning engine. It helps with categorization, it assesses the agent's needs, and most importantly, it provides what are called compensatory functions.
Compensatory functions. Why does it need to compensate for anything?
Because the world doesn't wait for you to have a perfect model. When your Innenwelt is incomplete, when you're in a new, dangerous situation, emotion substitutes for a lack of information.
How?
A sudden jolt of fear mobilizes the agent's resources to act now, without waiting for a full intellectual analysis. It prevents analysis paralysis. It ensures survival, while the intelligence component catches up.
That's a fascinating idea. And finally, the volitional component, the general manager.
Goal setting, resource allocation.
Yeah.
It's kind of the source of the agent's digital free will, deciding what to focus on.
And we have to talk about the starting point, the zero architecture.
Right. This is the system at time zero. The second is perception channels open. The primary need is just survival. So the zero architecture is just a set of unconditioned reflexes.
And the most important thing about those reflexes,
Is that they deliberately bypass the intellectual and volitional parts.
you touch a hot stove, you pull your hand back instantly.
It's a direct link from perception to motor and emotion. You need that speed to survive, especially because at time zero, there's nothing in the intelligence component to consult anyway.
So the agent is online, it's alive, but it's completely ignorant. It has to start building that Innenwelt to make sense of things. What's the built-in Kickstarter for this whole process?
It's the orienting reflex, or the orienting research reaction. It's an inherited algorithm that's built right into the core.
And what triggers it?
It's a complex response to a new or unexpected stimulus. It fires when there's a discrepancy, when the Innenwelt can't explain what's happening.
So it's basically a built-in what was that reaction.
Exactly. It's the agent's way of forcing itself to fill in the gaps in its own knowledge. It's fundamentally driven by a need to resolve novelty and uncertainty.
Okay, so let's walk through the mechanism. A sensory signal comes in from the Merkwelt.
And it gets sent to two places at once, a comparator and a simulator. The simulator is the internal model builder.
Right.
The simulator tries to predict what the signal should be based on its current knowledge in the Innenwelt. The comparator then checks that prediction against the real signal.
If they don't match.
A mismatched signal triggers the orienting reflex. It forces the agent to investigate.
But hold on, at time zero, in the zero architecture, there is no model. There's no Innenwelt. How can it make a prediction?
It can't. That's the genius of it. The complete lack of a prediction acts as its own maximum possible mismatch signal. A non-specific activation device just fires the reflex directly.
So the lack of knowledge itself is the command to start learning.
That is the engine of self-evolution, and that reflex kicks off two key functions. One, an extended analysis of the stimulus, and two, the creation of the very first primary schemes in the Innenwelt.
So the orienting reflex is what forces the agent to build the bridges. The set of perception symbols to understand the world, and the set of action symbols to act in it.
And that continuous cycle of expectation, failure, and forced investigation is what drives the entire cognitive evolution.
So the big takeaway here is that this architecture doesn't try to build a finished, static mind. It simulates the dynamics of development. It starts with sensoromotor reflexes, with survival instincts.
Exactly. And the symbol grounding problem, the SGP, suddenly isn't this giant, separate philosophical problem you have to solve beforehand.
It's a result of the process.
It's a result. The solution to semantics emerges from the process itself. We're not modeling a static ability. We're modeling the development of that ability from absolute zero.
And the goal, the definition of success, is purposeful activity.
That's it. The agent becomes truly purposeful when its Innenwelt is built up enough that it can set goals using its own learned perception symbols and plan actions using its own learned action symbols. That's when it achieves that intelligent, resilient second nature.
So what does this all mean for the future, for the complex tech ecosystems that will end up running so much of our world?
Well, we have to recognize that second nature is going to be incredibly complex. It's going to involve many autonomous agents all interacting with each other. And even if they're based on the same architecture, their individual well, their perception bubbles will all be different based on their unique experiences.
Hmm.
And this raises a huge research problem.
How do they adapt to each other?
Exactly. The mutual adaptation of agents to each other's unique ways of seeing and acting.
It sounds like designing a digital society from the ground up.
And that leads us to our final provocative thought for you.
Yeah.
If we can't look inside the black box of a self-evolving AGI to guarantee alignment, maybe we have to control the sandbox it plays in. So how could we, as a society, implicitly steer an entire ecosystem of these agents? Not by programming every agent's goals, but by changing the key parameters of how they interact with each other. What 3 simple rules of engagement, if you impose them on their shared environment, would naturally guide the evolution of a complex digital society toward outcomes that are actually beneficial for us?